Welcome to the Explainer. Today, we are opening up a case file on one of the biggest, most mind-bending mysteries in all of computer science. We're going on an investigation that has had the smartest people on the planet scratching their heads for decades.
And it all boils down to this, a question that sounds almost too simple. I mean, of course, some problems are harder, right? But what if they're not? What if the problems that we think are impossibly hard are just misunderstood? This is a detective story about the very nature of difficulty itself.
Okay, so let's dive in. Every single day, computers are solving problems for us, right? Getting you from point A to B, figuring out what movie you should watch next. But behind the curtain, not all of these problems are created equal. Some are, for a computer, a total walk in the park. Others, well, they're more like a grueling, endless marathon. Let's make this real for a second. On the left, we've got what we call easy problems. Finding a name in your phone's contact list, your computer does that in the blink of an eye. Or, hey, checking if a finished Sudoku puzzle is actually correct? Super simple. But on the right, that's where things get wild. Finding the single most efficient route for a delivery truck hitting 1,000 different stops, or trying to solve that Sudoku from a blank slate, that is a whole different ballgame, where the number of possible answers just explodes into the trillions. And this, right here, is where our mystery really kicks off. The question isn't just, can the computer eventually solve it? Because yeah, given enough time, we're talking maybe billions of years, it probably could. The real question is there a clever, efficient shortcut we just haven't discovered yet? Or are these problems fundamentally, provably hard, with no shortcuts, no matter how clever we are?
So to get a handle on all this, computer scientists do what any good detective would do. They line up the suspects. They group problems into what they call complexity classes. And by figuring out which class a problem belongs to, we can start to understand its behavior and just how much of a fight it's going to put up.
First up in our lineup, we have suspect P. This is our easy group. Problems in P are the ones we basically consider solved. As the problem gets bigger, the time it takes to solve it grows at a really predictable, manageable rate. That's what polynomial time really means. You can think of this as the good guy class. Next up, probably the most famous suspect of them all, NP. Now, these are the easy-to-check problems. Think back to our Sudoku puzzle. Finding the solution from scratch is really, really tough. But if I hand you a completed grid, you can check if it's correct in like 2 seconds. That is the classic sign of an NP problem. The answer is easy to verify, even if it's incredibly hard to find. And finally, we meet our biggest, most mysterious suspect, PSPACE. This class holds all the problems that can be solved with a reasonable amount of computer memory, or space. But here's the catch. It makes absolutely no promises about time. A problem in PSPACE might take the age of the universe to actually finish. But hey, at least it won't crash your computer by running out of memory. So here's our lineup. We're pretty sure that anything that's easy to solve is also easy to check. And anything that's easy to check can be solved without needing an infinite amount of memory. This creates this sort of nested relationship, like Russian dolls. P is inside NP, and NP is inside PSPACE. The billion-dollar question, though, is this. Are these dolls actually different sizes? Or are they all secretly the exact same doll? And that brings us right to the heart of our case. Are all the problems that are easy to check, the NP problems, actually the same set of problems that are solvable with a reasonable amount of memory, the PSPACE problems? Is there a gap? Because if they're the same, it could mean a lot of problems we think are hard might have shockingly efficient solutions. But if they're different, it means we've found a fundamental wall, a true limit to what we can compute.
So how in the world do you solve a mystery like this? You can't just throw bigger, faster computers at it. No. To crack this case, you have to analyze the evidence itself. And in the world of logic and computer science, the ultimate form of evidence is a mathematical proof.
This is where we call in the forensic team. It's a field called proof complexity, and instead of looking at the problems, these researchers look at the proofs about the problems. They ask a really simple but profound question. How long does the argument have to be? How much paper do you need to prove something is true? It's all about measuring the size of the evidence.
And this quote right here, this is the whole strategy. If we could prove that for any problem in, say, PSPACE, the shortest possible proof of its solution is always ridiculously, astronomically long, way longer than any proof for a problem in NP, then we've done it. We've proven the classes are different. That would be the smoking gun. So, if the length of a proof is our key piece of evidence, What happens if we can shrink it? This question is leading to a totally fascinating new forensic technique, one that could seriously change the game. You know how you can zip a file on your computer to make it smaller? Well, believe it or not, researchers are trying to do the exact same thing, but for abstract mathematical proofs. Using these powerful techniques like grammar-based compression, they're searching for repeating patterns and redundancies inside a proof, a kind of logical grammar, to see if they can create a much shorter, more elegant version. Okay, so let's walk through the logic here. Step 1, you take a long, complicated proof for some problem. Step 2, you run these advanced compression algorithms on it, looking for those hidden patterns. Step 3, boom, you get a much shorter, much tidier proof. And that leads to the fourth and most critical step, the big question. If a problem we thought was super hard actually has a really short proof, does that mean it was an easier NP problem in disguise this whole time? So, after all this digging, all this forensic analysis, where does our investigation actually stand? What have we figured out about this great mystery of NP versus PSPSE? Well, here's a quick look at our case file. The core mystery is still unsolved. Is NP really a smaller, easier class of problems than PSPACE? Our suspects, as you know, are the complexity classes P, NP, and PSPACE. Our main piece of evidence is the length and structure of logical proofs, and our most advanced forensic technique is this incredible idea of proof compression. We're getting closer for sure, but the case is not yet closed. Now, this isn't just some dusty old theoretical game. The question of whether NP equals PSPACE is one of the biggest open problems in all of math and computer science. And while we don't have the final answer yet, these powerful tools of proof complexity and compression, they're giving us the best clues we've ever had. And this brings us to the final, crucial takeaway. The answer to this question, it has massive consequences. If it turns out that NP equals PSP, it could totally revolutionize fields like AI, drug discovery, logistics, you name it. But if they're not equal, it confirms that there are fundamental, unbreakable limits on what we can efficiently compute. This whole investigation is about defining the very boundaries of the possible. So we'll leave you with this. When we finally do crack this case, what part of our world do you think changes first?